Okay, this is recording for 7-3. Uh, so we've talked about ratios, we've talked about proportions. Now we're going to talk about similar polygons. In order to be similar for two polygons, they must meet two conditions. The corresponding angles must all be congruent, which is here, and the corresponding sides are in proportion. And that means that they all reduce back to the same exact ratio. Just like with congruent figures, when you state two figures are similar, their corresponding vertices must be listed in the same order. Remember when we did triangle congruency and we would say triangle ABC, whatever we said first was okay, but then when we said what triangle it was congruent to, we had to make sure whatever angle was congruent to A was first, because that's what we had put first, and then what was B went second, and so on. You're going to have to do that, make sure you do that with the similar figures as well. The scale factor is the ratio of the lengths of the two corresponding sides. So just to kind of talk about that for a second, I have two similar triangles here. What I basically did was the dilation you did in class today when we practiced dilations. For that, I have ABC as my original triangle, A prime, B prime, C prime as my dilation. I dilated by a factor of 2. So you can see that all the angles are exactly the same. So that meets that first condition. And then that all of the sides are in proportion. 2.19 doubled is 4.38. So this has a scale factor of 2 to 1. Okay, so they're exactly the same. One is a smaller version of the other. The congruent angles, notice the angles are exactly the same. And the sides, the side across from the 42.07 angle is twice the other side across from the 42.07 angle. So I would say here triangle ABC is similar to triangle A prime, B prime, C prime. Again, making sure my order keeps the corresponding parts together. In this example, you can see we have quadrilaterals. I probably should have said here A, B, C, D is similar to, and what that's going to be is like the squiggle. That means similar to, and now I'm going to make sure I put everything together. E, F, G, H. So angle E corresponds to angle A, so this one will also be 60. B corresponds to F, so this is 100. C corresponds with G, so that one is 90. And D and H correspond. Now, I can tell here I have 250 degrees. It's a little late, so if I calculated that right, that's 250 degrees. In a quadrilateral, I need 360. So this must be 110. So must this. If you don't know how I got that, check in with me. That's that 180 n minus 2 deal. So I've answered. I got angle E, angle G, and angle B. The scale factor I can find by finding two parts that are corresponding in the same place. So I'm going to use these two. So honestly, 4 over 12 or 12 over 4, either one. Doesn't matter to me. So you could say a 1 to 3 scale factor. If you said a 3 to 1, you are also right. So I'm good with either one. They both make sense. All right, so to go to EH, EH is going to correspond with AD. It's a 1 to 3 ratio, so 5 to what would reduce me back to a 1 to 3 ratio? 15. I'm getting that because basically every side of ABCD was multiplied by 3 to get to EFGH. BC corresponds with FG. So again, I need 1 to 3. So that means BC would be 2. If you're unsure too, the other way you can do it is set your scale factor and set up the proportion. So if BC is the missing side, that goes with the ABCD figure, and FG is this side. And you could cross multiply and solve. You could get your 2 that way as well. AB, in order for this to reduce from 1 to 3, I need AB to be 7. So sometimes you can just kind of logically go through them once you have it. If you're having trouble with that, you can go to the proportion every time. In the next example, I told you they were similar. Quadrilateral ABCD to A prime, B prime, C prime, D prime. So you can pause and try and do the scale factor yourself, and then come back and check and see if this is right. For the scale factor, again, I'm finding 2 sides where I have numbers in both. The y and the 12, that's not helping, that's not helping. So right down here, the 50 and the 30. So you could call it, again, a 5 to 3. I'll write it a little differently this time. Or a 3 to 5. You're right either way. So for x, okay, I need this to reduce back to a 5 to 3. Okay, well 5 times 6 is 30, so 3 times 6 is 18, so x is going to be 18. If you don't follow my logic there, do the same thing again. 5 over 3 equals 30 over x. When you cross multiply, you'll get 5x equals 90. And when you solve that, you'll get x equals 18. So that's my x. For my y, okay, so again, I need y to 12 to reduce back to 5 to 3. Well, 3 times 4 is 12. So if I took the 3 and multiplied it by 4, I need to do that to the 5. So the y is 20. And the z, that's a little trickier, a 5 to 3, so I might need my proportion there. Sorry, this pen's being crazy. Okay, equals 22 over z. Okay, so if I cross multiply that, 3 times 22 is 66. Divided by 5 gives me z is equal to 13.2. When you did the ratio of the perimeters, I will tell you that should come out to be 5 to 3. If you look back at your properties of proportion and look at the number 2 on that first slide in that notes, that's why. I can talk about that more in class. The last example here is the same idea. If you were able to get that first one, I think you can do this. So I'm not going to go over that again, but if you want me to check it in class, if you want to try it and see if you got it, the ratio of the perimeters should always reduce back to the scale factor. It comes from that property of proportion. So those are your 7-3 notes.